from California, where it's 9 o'clock. I am Francisque Savignan, the founder and CEO of Epartrade, and I'm with Judy Keane this morning, the co-founder of Epartrade. Good morning, Judy. How are you doing?
Good morning, Francisque and everyone.
Excellent. We have the great Brad Gillie, who is going to be hosting our webinar today. So, Judy, we got something special today. We have a double feature, right?
Yep, our first double feature, and we are excited and fortunate to have Zeke with Ferrea Racing Components and also Luke Wilson for Piston Racing, some of the best engines around.
Excellent. And so, and at 10 o'clock, we're going to be joined by Leg Speed from Total Seal Piston Ring and Charles Navarro from LN Engineering. And we're going to be talking about cylinder head coatings. So stay with us. It's going to be a long program, and it's going to be hosted both sessions by Brad, who is a terrific host and has been, working with us for a few months now, starting with Online Race Industry Week. So one important thing, and I want to reinforce that we have created and we produce those tech webinars weekly for you to engage. So please use the chat button, ask all the questions you want. The guys we're bringing on today are actual expert and their expertise is priceless. So feel free to ask them as many questions as you wish. That is very important, right, Judy?
That's right. And keep in mind, both Total Seal and Ferrea, they're showcasing on here. So when buyers register and they are on this platform, it's really very similar to walking up and down aisles, looking at the latest and greatest in the racing products and technology. They're here for you. So if you have interest, what you do is you hit that request more information button with questions, or if you want to become a dealer, and you two connect. I'm often asked how this platform is very similar to a trade show.
Absolutely. Very good. So I see we got Zeke and Luke on. Good morning, gentlemen. So Brad Gillie, on to you for the next hour.
Well, thank you very much, Francisque. Really appreciate that. And as Francisque mentioned, as Judy mentioned, this is interactive. This also involves you. So if you have a question at any point throughout, just please feel free to use the chat feature, and we will do our best to get all of the questions out there. But I do want to welcome Zeke, Urrutia, as well as Luke Wilson. And we appreciate both of you gentlemen coming on here today. Looking forward to talking about Valvetrains and Valvetrain components and all of those good things. Zeke, I'll start with you. How are you doing today?
Good morning to you, Brad. How are you?
Fantastic. Thank you. And Luke, you're the owner of 4 Piston Racing. Thank you for coming on with this as well. How are you doing?
Doing great. Appreciate it. Appreciate the opportunity.
Well, awesome. Well, as the questions come up, if I'm directing a question to either Zeke or to you, Luke, and either one of you feels a need to jump in and maybe add to whatever that part of the conversation is, by all means, please do so. This is wide open and this is very interactive, but I don't want to necessarily leave anything on the table if there's some great things that we can talk about. So Zeke, if we can just start with you first of all, and just tell us about, everything that's going on with Ferrea Racing Components, and really more specifically, what we're going to be talking about here today.
Yeah, so Ferrea Racing, I mean, we're a 50+ year company, right? Business as a whole has transferred a lot of what we do initially to Valvetrain components. Our main business is valves. We've been manufacturing valves since the 70s. And that was our core business, where then we initially started building other components around the valves that work within the cylinder head to help out and achieve performance and reliability, as well as better components that we've seen in testing that we could create around our valves. And that's really where the story really begins with us, is knowing where our background comes from. And the 2 owners that are part of Ferrea, they were engine builders. I mean, they were part of Chrysler, they were part of Ford, they were in their engineering departments. They won many championships in Argentina. Initially, that's where the company first started. And then it obviously came here in the 70s. But their background really focused on mainly cylinder heads and cylinder head Valvetrain components. And then the engine was looked at as well as the entire build, but mainly looking at building and creating, and actually the owner itself, Horatio Ferrea, he built cylinder heads himself back in the 60s and 70s and designed them for a lot of these race teams.
Luke, let's ask you, I mean, as far as using the Ferrea components and all of that in your normal day-to-day, I mean, first, you know, if you would just kind of give us an overview about four-piston racing and how Ferrea helps you.
Yeah, absolutely. Ferrea really was a really instrumental in us even starting our business. We started this as just out of passion for cylinder heads. We initially didn't build a lot of engines to start with. We wanted to just do cylinder heads, and you're always looking for a company that can deliver the products that you need when you need them, and that has good quality control. There's nothing worse in the racing industry than, you know, being on a time crunch and opening components and finding out that they aren't what you thought you had, or that you have flaws that you have to address. And Ferrea always has given us the best right out of the box quality, and it goes a long way. When we're speeding along or we're on a deadline, we have to have those things really exactly what we expect. And so we've stuck with Ferrea simply because of reliability and consistency of manufacturing. We know what we're getting, and we know how we can set our schedule based on the fact that we know we don't have to worry about that aspect of the engine anymore. That's going to be right. So our business transitioned from cylinder heads to more of designing racing engines for specific applications, because we're in a market, this multi-valve market, that's growing. This is the type of vehicles we all have now. A lot of 4-cylinder, 6-cylinder, multi-valve overhead cam engines, and they're raced all over the world in all types of different applications: road racing, hill climb, dirt cars, anything you can imagine. All over the world are using these engines. And you know, I would say that there's kind of a shortage of engine builders in that market that specialize specifically in that. And so we saw an opportunity to go into that and really just bring that level up, bring it up to a motorsports grade product and something that people can rely on. And Ferrea was a big part of that.
Well, Zeke, when it comes to MultiValve Technology and what Ferrea is doing right now, can you give us a bit of an overview about what you guys are working on, and more specifically, you know, how it might even benefit a lot of our audience here today?
Yeah, so a lot of the cylinder heads, obviously you look at the past, from going from 2-valve to 4-valve. 4-valve cylinder heads, multi-valve overhead cams type cylinder heads, have really hit the ground here. And when you look at hitting the ground truly in the US, multi-valve cylinder head technology came about in the 90s. I mean, if you look at the early to mid 90s, that's really where we focused a lot in getting our Valvetrain components in a lot of these engines. Whether you had drag racing, whether you had a circle track car, or whether you had an open wheel car, you know, we focused a lot into the multi-valve technology in those times. And the main aspect was because we saw this coming in the early 2000s to mid 2000s, this technology. Obviously today we're working a lot with multi-valve cylinder heads, but the forecast and what we saw back then and what we see today, especially with the electronics, the data log systems that we run today, we're at a point today with multi-valve technology that, I'm not saying it's easy, but it's easier than it was 15 years ago to really make like a tremendous amount of horsepower with these engines. And it's become basically now the 2-valve technology against the 4-valve technology. And a lot of aspects, people have embraced the 4-valve technology because they see the gains that you can get with these cylinder heads, as well as the reliability. I mean, you look at, just an example, look at size of valves. You know, mind you, there's more valves in an engine on a multi-valve cylinder head compared to a 2-valve. But you look at the overall distance from where a valve-to-valve clearance is from a larger 2-valve cylinder head to a 4-valve, you can control the engine so much easier today with the 4-valve cylinder head overall with all the data log systems. And I don't take anything away from the 2-valve technology because it still exists today. But in today's world, Ford has done an exceptional job of coming out with really great 4-valve technology. GM is just starting to embrace it a lot into a lot of different applications. They're still racing 2-valve technology, but into the 4-valve technology, it just becomes where Ford has really captivated that technology in the V8 segment. You know, if you look at the domestic market, the Coyote, you know, there's, you know, tons of videos that you can find online, and you know, people have been doing testing and comparing, you know, both the Coyote engine and the LS platforms, for example. Great platforms, very popular in our market, but you look at really where is the aspect of the flow characteristics of the cylinder head and how well the dynamics work. And the 4-valve is tremendous to work with. And it's really, I think, here to stay, obviously. I think the 4-valve technology would enhance different avenues, even when you go down the road and you talk about hybrid systems, you know, inside vehicles and efficiency. That's where a lot of the racing, road racing, if you look at Le Mans, 24 hours of Daytona, a lot of these endurance type races where a lot of these different race teams have seen the improvement with hybrid systems with 4-valve technology work so well.
Now, Luke, on that aspect too, there are a lot of different people who have different schools of thought of what they like. There are some people who want, give me the latest and greatest. I want everything that's going to work. I'm all about the new technology. And there are some people saying, all right, wait a second, let's go with what we know. I'm going to want something really bulletproof under the hood, a long time proving technology. Let's find a way to make that better. So when it comes to the multi-valve technology and the engines that you're working on and that you're building, what do you say to a racer? What do you say to a racer who is maybe more from the old school and says, hey, let's just go with what we know?
Well, we have to cater to both. So we're still doing, we're doing 4-valve engines that still have mechanical injection, constant flow systems. We have then, people that have moved from, it was like 10 years ago, we were trying to get people to stop looking at the carburetor and start looking at electronic fuel injection. But I have some carb guys that would like to teach me a few lessons. And it's just, it's all relevant. And now today we deal with it with direct injection. We're just on the tip of the iceberg as far as understanding how to extract the maximum amount of horsepower out of direct injection. Engines, they're very different. The cylinder heads are drastically different. We have to think about the valve seat angles totally different. The airflow just moves through the port differently, and it doesn't have fuel in it. So we have to be looking forward, and we have to, go ahead and embrace this new technology and get ahead of it, because if we're not, we're going to be behind. At the same time, we still do have to take care of, there's still a lot of engine development to be had with older technology. I'm still on the dyno right now with a constant flow injection setup for a USAC midget, and it's a new engine that's introduced to the series. So there's still horsepower to be found, and you need to focus on where you can maximize your profits, and we all want to win. And if you can win and you can make reliable products, then you're going to be around for a long time. But you can't ignore new technology, that's for sure. This direct injection thing is changing, however, and it may be here for emissions or idle, a lot of idle emissions, but it also has some performance advantages as well, as far as throttle response and instantaneous response and fuel burn. And in endurance racing, fuel burn is very important. We have to make sure if we can get an extra 2 laps where someone else couldn't, it could be the difference between winning and losing. So we have to embrace this new technology and try to understand it and squeeze every little bit we can out of that thing.
Yeah, and even when you look at just porting wise, right? And this is where, you know, obviously Luke and the team out there, that these guys do a lot of the cylinder head flowing characteristics, as well as looking at the dynamics of the ports. Well, something it's been a challenge for us on the single port exhaust, you know, areas on a lot of these typical 4-valve cylinder heads. We've had to adapt to a lot of that. It's been a challenge because in a lot of cases, you can't get in there and do too much work to these single port exhaust areas. And you really have to, you know, look at and go back and say, all right, should I really increase the size of this valve? You know, should I really look at just putting a standard size valve in this? Should I change any of those dynamics, whether it will increase or decrease some of the flow or hurt, you know, that area? Because the fact that, you know, most guys say, well, I start, you know, with, you know, typical engine, let's just call it a 4-cylinder type application. You know, I want to make 300 horsepower on it, turbocharged, you know, 350 horsepower. And then it evolves to, you know, I want to make 500, you know, and then it evolves to, I want to make 700. And that's where we always think about a little bit further down the road. You know, where will that guy be? Will that guy be at 700? Will he be at, you know, 1,000 horsepower or 1,200? And that's where these dynamics of these particular cylinder heads have to take a big consideration in really thinking about what avenue to really take, and to know that size of valves really make a huge amount of difference in those type of cylinder heads. And Luke can probably, you know, talk about a little bit more on what they've seen, especially on those platforms.
Yeah, absolutely. And you know, we take 4-cylinder head development, or 4-valve head development, similar approach. Like we look at a head, and we have limitations in these castings, which are the water jackets and the valve angle, because we have typically valve angles that are much different than maybe you would have seen in a perfectly race developed cylinder head. So for packaging's sake, we may have a 25-degree valve angle, and we have a small bore engines, and you have the valves running really close to each other, running into each other. So increasing the valve size can be a challenge, and we have to weigh whether or not the 10 or 12 CFM we'll get from an extra millimeter of valve size is worth losing, you know, the camshaft center line and the valve timings. The valve timing's critical. So a lot of times these engines historically have had oversized exhausts related to the intake. So we will still go into cylinder head development with the idea that we want to get the most CFM possible. And we need to size the seat, the throat, the port, you know, based on what we can physically fit in the head. There's a lot of water jacket in these new heads. Those single port exhaust heads, they're all about flowing water through the headifold, or the molded in exhaust manifold into the head. And they do that for emissions. They're trying to bring the EGTs down. They're trying to heat the engine up really quickly. So when you first start the car up in the morning, the thing comes up to temperature rapidly, and it's a lot easier to deal with the fuel burn. So a lot of that stuff for emissions can hurt us on the performance side of things when we just get into a racing application. So we're constantly trying to balance valve size versus what port we can actually fit in the cylinder head versus our RPM range. You know, we're taking engines that have an operating range up to 6,800 RPM, and we want to turn 9,000 or 10,000 or 11,000 RPM. We have to focus that port design around what the particular racer's operating range is. So valve size is a huge thing that we play with. We may have on a naturally aspirated engine a valve that's so big that it's nearly running into the side of the bore, and we have to figure out, is that shrouded up so much that it hurts us, or does it not matter? We just need to get airflow and fuel into this thing. Or is it a turbocharged application where the valve timing is so much more critical than the few CFM we're going to gain from the bigger valve? So we have some 120 cubic inch 4-cylinder engines that guys are making 1,500, 1,800 horsepower with. It sounds crazy, but we got to let the turbo do its job. And the valve timing is so much more critical than maybe the 10 or 12 CFM we would gain from a little bit bigger valve. So we have to weigh that out. If it didn't have the turbo on it and it was a naturally aspirated engine, we're pretty well always fighting to get the biggest intake valve we can in there. And lucky enough that the exhaust ports they're sized, pretty large really for those types of 4-valve engines, because they used to use that for emissions as well. So they've got oversized exhaust ports, and that's not the rule. That's most applications are like that, but not all. But yeah, valve size is critical. I mean, we're constantly playing with that stuff.
Yeah, and I actually think that both of you gentlemen just answered one of the questions that did come in from the chat, which asked what are the benefits of oversized valves and multi-valve heads. And it's not always bigger is better, but it's just got to be the right thing for the right application. If you can go big, great, but you can't always. Is that fair?
That's fair.
Yeah. And honestly, we see a lot of mistakes in this. We'll see small shops or engine shops that just, or just customers in general, they go to a larger valve just because it's larger. And they want bigger is better, right? So a lot of these heads have small seats in them compared to the valve. There's not a lot of room to put a bigger valve, so you've got to put bigger seats. But they'll put a bigger valve into a stock port head or a port that was designed around a smaller valve. And if let's just say we had an 87% throat on a head that we were working with, and we just throw a bigger valve in there, we may be putting ourselves at a disadvantage for camshaft center line when we really had a lot more work to do to maximize the airflow out of the valve that we had, where we could start working towards a 92 or 94% throat, and get more performance out of a smaller valve size. So you have to size these things proportionately to the port. And really, we're trying to slow airflow down in these 4-valve ports a lot. You have this crazy valve angle. They're not stood up like a Formula One engine. They're not stood up like, where the valve is very straight. So we have a laid flat port, and the airspeed's coming in so fast that it skips over the short turn and hammers into the back of the valve. So a lot of times we're trying to slow that air down. Everybody talks about, I want a high velocity port, a high speed, small port. Most of these 4-valve cylinder heads, very laid flat, very short port length by the time we consider the whole induction tract. And we've got to slow that air down in order to make horsepower and have a good combustion process.
Yeah, we just had another question come in and said, how often do you go to smaller valves? And certainly want to throw that at both of you, but maybe are there applications where you would say in this type of engine, or with this type of intake and things coming in, typically you would want to look for something bigger? Or I know you had mentioned turbos and different things like that. maybe this type of engine and this type of performance is where you might start looking for smaller, but you're going to also look at all these other aspects. And Zeke or Luke, whoever wants to take that.
Yeah, I mean, just in the aspect of, let's just talk about 2-valve, pro stock application. Everything obviously has gone fuel injection. Even in that, where you're not having a multi-valve type configuration on the cylinder head, they've even gone to smaller exhaust valves and bigger intake valves. This progression really has been the trend in the past 4 to 5 years, where they've found this extra horsepower on the exhaust side, as well as opening up larger and larger intake valves. I mean, if you look at just size of valves, typically on those engines, obviously for pro stock, they've been trying to get every inch out of these motors. You're going from point A to point B on a distance, and we need to literally get everything that we can out of this engine. The fact is that we used to run, say, a 1.900 exhaust valve. Now we're playing with 1.820s, 1.830s, 1.840s, and intake valves have gone extremely large on those engines. So they've obviously, in that type of technology, they've found that the intake needs to get as much as it can out of it. And the exhaust can help itself, but restricting some of the exhaust will help it create a little bit more flow on the back end of that exhaust valve, and in turn create a little bit more upper part of the engine horsepower. And this stands to be true on the 4-valve technology. You look at the aspect of, we used to run large valves. Let's just call a 2JZ inline 6-cylinder engine is literally the stepping stone of sport compact racing, you know, and what it's come about and what it's evolved into and what it is today. And we're still learning about it, believe it or not, on that platform. But we used to run 2mm oversized intake and exhaust valves. In today's world, we're going back to standard size on these 6-cylinder inlines. You know, there's either a 3-liter or 3.4-liter type engine. And we're finding the same amount of horsepower or more with standard size valves on these type of motors. So again, what I think is really the main aspect of this too is the tunability and the data log systems that have implemented to allow you to go and play along with all these different parameters on these engines to help out with going with the smaller exhaust valves. Turbos have gotten, you know, if you look at turbocharged engines, they've gotten well efficient. You know, we used to fight the fact that just retain oil in a turbocharged engine on the turbocharger. You know, that's no longer the case anymore. You know, they're very efficient, very well made. That avenue also, where you look at those applications, it's helped it out tremendously too, where it helps you look at the size of the valve and diminishing the sizes overall. And in turn, it makes the engine just a lot more reliable, because you look at a size of a valve and distance wise from, you say a 2500 intake valve, and you look at a really small stem on a valve, your distance, you're getting farther away from that center point of that stem of that valve. The further away you get in there, we call it a seesaw effect. So that valve will flex a lot more in that area and will not be reliable. You're going to get a lot of bouncing off the seat. The valve float will maybe start occurring because the valve is just not comfortable in there. So the smaller areas of that head portion of that valve now has made that valve a lot more stable overall.
Interesting. Couple more questions from the chat here. We've got a few of them coming in, so definitely want to get to as many as we can. Which, by the way, Mike Norman had said he definitely found smaller exhaust valves and ports has helped them in their application. James McMahon wanted to know, in a NA valve, which has the fuel sprayed directly at the back of the intake valve, what grit finish is best for the port? Supposed to say full valve, 4 valve. That makes sense.
Yeah, I mean, everything we do, we used to hand port heads. We wore our wrists out doing that. Everything's CNC now, and we do see different pick patterns and different textures having an effect. And now you're seeing golf ball ports and things like that, which you won't see us do. These aren't golf balls. We're not playing golf. But you can change the dynamics of the port with this texture, even with the golf ball texture. It's not always a bad thing. But you know, we have this boundary layer that attaches to the port. So if we're talking about port texture, and we've done a lot of back-to-back dyno testing with mirror finished, almost mirror finished, drastic steps in the pick pattern of the CNC, the dimple port, the whole spectrum. We've done a huge amount of back-to-back testing just to figure out what does work best. And it depends on the fuel, it depends on the RPM, it depends on the port itself. What is the airspeed? Where is the fuel being injected? They're all variables, but for the most part, we have this boundary layer that attaches to the port wall. And then we have faster moving air that rides on that boundary layer. And you can affect the thickness of the boundary layer with the port texture. So typically we want some type of texture just to soften that boundary layer and make sure that we have a good controlled boundary layer. We get our air speeds in the port. So we don't have erratic airflow in specific areas. I will say that, you know, a lot of times in these 4-valve heads, we have this limitation of the water jacket that's really close. And so we may need to have a port, you know, a port wall that's only 30 thousandths thick. And think about engines that run 75 pounds of boost. we need that 60,000 stick, but let's just say it's a naturally aspirated engine and we're getting that close to the water jacket. Imagine putting a golf ball, a dimple, I'll stop calling it golf, a dimple wall in that. You have to shrink your port. You're already limited. You have to shrink your port in order to get the dimple wall in it. So not only are we losing some real estate where we need it, but we also now have this dimple wall that actually creates a thicker boundary layer. And where this will be an advantage is if you have way too much port size for your engine. So if we can't get enough port in the engine, that's going to hurt us bad. We're going to see a really poorly performing engine if we put this dimple wall in there. The port is already too small and we're just making it behave smaller. If we have an engine, let's say we had a 2-liter engine and we put a cylinder head from a 2.5 liter that needs to turn 11,500 RPM, that's just way too much cylinder head. That dimple port behaving smaller may be an advantage and we may see gains. So for the most part, we stay away from that. We're looking for the proper port shape, the properly designed port for the specific engine. Texture wise, you've got a lot you can play with there because there's not a huge amount of difference. You've just got to control that boundary layer that's attached to the wall and its thickness and worry about the air that's riding on top of it. And I hope I answered that question.
Zeke, you have anything you want to add to that at all?
No, I mean, the only thing is that golf ball effect. I mean, we feel the same way where that the golf, the little pivots or the small little dimples that you look at and put on these typical cylinder heads today, it's cute. I mean, I think in aspects, it's a good selling point, I think, for some guys. But we looked at it as well, and we actually look at some dynamics in house, and the fact that those dimples can actually spread the aluminum on a turbocharged engine and actually form canals, believe it or not. This happens already with a ported head without having a dimple, and having those effects can inhibit creating these channels within the aluminum itself, on some of these aluminum cylinder heads. So very dangerous, to do that because you're already, you're fighting against, pushing 75, 100 pounds of boost on a turbocharged engine, and the aluminum is screaming. I mean, it's yelling at you, like, what are you doing to me? You're trying to, squash me in here and then spread me apart, so that's something that we feel the same in the fact that, you try to look at these dynamics and thicken up these areas as much as you can, but you're left with environments that are just so crucial on these heads that you need to work in these parameters,
Well, you mentioned aluminum. Let's talk about the materials and materials for valves. What material valve is best, say, for a drag racing engine? Right.
So great question. I mean, this is all depending the application. When you look at titanium, for example, great material, excellent material. People think that, titanium valves is the all and be all. Everybody wants titanium valves. It's the best. It is the best, but in certain applications. And those applications really have to look at with the fine comb tooth, with the fact that you really have to see if that application either has some type of fuel, so say you're running gas, VP, for example, that fuel on a turbocharged engine on a titanium exhaust valve is a no-go. And the reason behind it is because of the amount of temperature that it creates. It will actually start diminishing the life of that titanium valve. And what will happen is it will actually start getting brittle at a certain point. So metallurgically, it changes the material very, very quickly. We get always asked about titanium valves. How long do they last in an engine? I wish I knew that answer. I wish I knew the lottery number too. I could be a millionaire today. But the reality is we don't know the answer to that question. And the answer is really elongation. When you look at elongation on a stem of a valve, especially a titanium valve, it gets to a certain point. And a certain point, for example, is whether that valve has elongation at 6 thousandths, 8 thousandths, 10 thousandths, 12 thousandths. Really, that valve is feeling uncomfortable in that area at that point. And you're lashing the motor now maybe 2, 3, 4 times, in the engine. It's time to replace it at that point. Seat wear is another indication on a titanium valve that can tell you that you need to replace it. We look at, a lot of the stuff that engine builders send back to me after doing a testing or a project or an engine that's run a few races. And we get back here, we call them pizza cutters sometimes, because the valve looks like literally a pizza cutter. The seat's completely gone on the valve. And the reality is it's either a compatibility issue, a spring problem, or an application problem in general, that they try to use this type of material in this application, and it's just not feasible. You just can't use it. And the flip side, stainless steel. Stainless steel is fantastic. Great for turbocharged engines, aspirated engines, in general, great for everything. The backdraw from stainless steel is obviously weight. You try to manage Valvetrain weight with some of these applications, and you're trying to get every single inch out of it. And a pound is a lot. It's a ton. I mean, talk to a Formula One engineer and throw to him, "Oh, I'm putting an extra pound on the Valvetrain." He's going to murder you, because he doesn't want to see pounds. He wants to see grams. He wants to see a couple grams at that, that really would perform the engine the way it needs to. But the good thing about stainless steel multi-valve cylinder heads is we're dealing with smaller stem valves. And the reality is we can build today a stainless valve comparable to a titanium valve in the same apples to apples comparing both. And we're not that drastic in weight-wise, where we can do other things within the Valvetrain itself to help out with the additional, let's just call it 8% more weight that stainless valve is adding compared to that titanium valve. But what you're going to be getting is the reliability from the stainless. You're going to be getting the longevity. I mean, all these factors really is what the stainless steel valve is today. And we still feel that the majority of the engines that are really built, unless, again, it's a drag race engine, you're putting the adequate fuel in there. And I'm talking alcohol, I'm talking E85, something that your EGTs are not more than 1200 degrees on the exhaust side. And let's look at titanium. Let's see if that is a viable source at that point to put that type of material in those type of applications to see if the improvement will be there or not. Guarantee it will be, because you look at, obviously, again, weight-wise, so you're going to improve quite a bit of the RPM range, as well as stability within the Valvetrain itself.
I had another question here. It's from Chris, and it's actually a two-parter. Oh, hang on, let me go. It scrolled up on me. Could a sodium-filled valve be produced if I wanted one? And are there any hollow stem or hollow stem and head options?
Okay, so sodium-filled valves, this is something that's come about in the market, and a lot of questions we've had because we've never pushed a sodium-filled valve in the market. It's great for an OEM engine, sodium-filled valves, very governed, where you see certain temperatures, regulated temperatures on the engine, no extreme environments that are really going on, again, where you're going from 1500 degrees to all the way up to 2000 degrees, and then going back down, throwing a shot of nitrous on the car, putting a turbocharger on it, a larger turbocharger, putting more force induction. Sodium-filled valves just don't react correctly when you put these type of applications together, because the sodium works at a certain point. You turn on the engine at 200 degrees, the sodium turns into liquid. And all the purpose of a sodium fill valve is to cool the stem and part of the portion of the head of the valve. That's great, again, for where the valve itself and the material you've used, sodium bases today, avionics that you look at, they're only good to 1600 degrees Fahrenheit. Once you exceed that temperature, now you're disrupting that sodium in there. So whether that sodium will stop traveling up and down the valve becomes a very large gray area. And in a lot of cases, it could stop traveling in that area because of the extreme temperatures. You have a hollow valve at that point. If that sodium inside there gets disrupted, and you don't want that. You don't want that hollow part on the bottom side of the head of the valve, because then again, it could be catastrophic on the engine. A lot of manufacturers, other valve manufacturers, get away with using less quality materials, and they throw a sodium, and now the valve becomes a little bit better. That's really not the answer to that question. We've really always stuck to our guns to go with a solid type valve when it has to do with turbocharged engines, engines that are extreme in environment, again, with nitrous, so on and so forth, as well as looking some dynamics with higher compression, normally aspirated engines. We've stuck to our guns with some solid piece valves. Now, where we've seen a lot of improvement is on the 2-valve technology. We have come out with hollow stem valves. We were the first to hit the ground in 2004 for the domestic market. We looked at taking a lot of weight out of a particular hollow stem valve in stainless at 11/32 seconds, which is a large valve for these small block and big block engines. And we increase, yes, the RPM, the performance of the engine. But again, most of these motors instilled today are put in, classes like stocker classes, classes that you can't touch the cylinder head. You can't do anything to the cylinder head, but you can put lighter valves in there. Angles, when you look at different designs of the valves, you can look at improving quite a bit of the design of the valve as well on the hollow stem to remove some of that weight and improve the engine, where a lot of these classes don't allow you to, go this avenue with hollow stem or not. So, just to kind of sum it up, we use hollow stem valves, but we don't touch anything in the hollow stem valves in a multi-valve cylinder head. Reason behind it, they're too small. There's no really benefits from it. We tried it with the 2JZ Super engine back in the mid 2000s. Number one, the cost factor was very large. And number two, no benefits from it, at all, very little, if any.
While we're talking about that, someone did ask about, has anyone looked at additive manufacturing to make a hollow or honeycomb fill lightweight valve?
Honeycomb, yeah, honeycomb film, we haven't looked at any of that. We really haven't filled it with any other material per se on a hollow part. What was the other question?
Honeycomb fill, let's say make a hollow or honeycomb fill lightweight valve, just maybe looking at additive manufacturing to produce that.
Right. Hollow, we've played around with hollow heads, hollow stems, we've played around with that a lot, and we have produced that for exclusively Pro Stock. We have not done that with any other application. And we were able to do that. Reason behind it is because, again, the size of the valves, they run a 5/16 stem valve. We have a lot of material to work with, but at the same token, you get X amount of runs out of it and you're done, at that point.
Luke, I'll direct this to you, and Zeke, certainly if you want to follow up as well. Tony Tobias wants to know, what part do engine dynos play in assessing performance improvements after modifying the cylinder heads?
It's absolutely critical. The biggest thing for us, a lot of shops have chassis dynos. We do too. We do both because you're dynoing the entire drive line, and we want to know that there's inefficiencies we can find in the drive line. But from an engine, that's for our race cars. For an actual engine development aspect, it's easy to work on the engine. It's easy to make changes. You're standing up. If you do this for a living and you're working on engines every day, you've got to be comfortable in how you pick up and move blocks, how you pick up and move cylinder heads around. You're moving 100 heads a day or something. You know, you're going to wear yourself out. The engine dyno is a tool that allows for two things. Number one, I'm moving my camera. Controlling the environment. Basically, if you have a good engine dyno setup where you control the airflow, where you control the temperature, where you can control the humidity, where you can isolate variables, then you can do good testing, where you can isolate movement on the engine stand. You know, there's all different kinds of engine dynos, and most of us engine builders don't have $1 million AVL dyno. Let's just be realistic. We have good equipment that's not what Formula One or IndyCar or some of these, you know, top tier places are dealing with. But we can really set up a nice test facility where we can control all the airflow and make sure we have good clean air, make sure we're controlling our temperature. I know I go dyno an engine here. I'm pulling air from a massive amount of space to make sure that we have, I could dyno all day with the same temperature, whether it's 15 degrees outside or whether it's 70 degrees outside. I'm pulling from a climate controlled massive amount of airspace in here. So we're going to get the same air quality. It's all about controlling variables. It's also about being able to work on the engine. So if I want to test camshafts, cylinder heads, swap things around, I'm standing up at work height. I can pull a cart away from the dyno. I can pull a new one up to it. It's all about efficiency and making sure you're not bending over a car, trying to work in the car, you know, under the hood, strapped to a dyno, or, you know, unstrapping it from a dyno and then putting it on a lift and restrapping it. You changed everything just by unstrapping it. Just loosening a strap and tightening a strap on a chassis dyno, you changed it. So it's all about just controlling variables and making it so that you can, in a time efficient manner and within the same conditions, dyno back to back. The engine dyno is critical. It's also laid back. The engine's not moving around like a car does on the chassis dyno. We're sitting behind a glass that you could shoot with a gun and, you know, rod fly at it. Nothing's going to happen to you. We're sitting outside, got a Coke and your lunch, and you're running the sticks and you're watching all your data. It's a nice environment. You don't have headsets on. You're just kind of sitting there and enjoying the day running the engine, and you can sit there and run programs on it. You can run endurance programs, break-in programs, and kind of babysit the engine and learn. But it's really still a lot of user interface, and how the effort you put in will affect the results you get out of it. So you got to be able to control all those variables. I've had dyno tests where we spent days on the dyno and had to throw everything we learned away because we goofed up something in our control. So it's a science experiment, and you have to control and have control of all those variables and make sure that you're accounting for everything. But it's critical in engine development. If you're not testing, then what are you testing on? You're testing it on customer cars that you don't have control. You're just going off what they tell you, and they could have screwed everything up, or they could have done everything right. You don't know.
Yeah, that makes sense. You know, Zeke, we've talked about cylinder heads and porting and polishing and valve materials and all of that. How about valve springs and valve spring technology? What have we learned in the last decade or so?
Right. So valve springs have really, they've evolved quite a bit. One in design, two in materials, processes, heat treatment processes specifically. Looking at finishes on the valve spring has been very critical. The big jump that we made and the leaps and bounds that we made on valve spring technology was really looking at particular dynamics on that spring and how this spring will react to having these different processes and finishes on the spring. You know, the wires have gone exponentially great. You know, you look at the inclusions on some of the wires from Japan or other companies, and they've become very, very good, you know, where you're getting clean wire all across, your manufacturing and not having to do too many QC steps within the process like they used to do back in the day. You know, you talk about 15 plus years ago. Really what we've enhanced quite a bit is to grab most of these valve springs today, and they have to be a good quality spring to allow you to get involved in this, but to run very close coil binds today. Today, it's not acceptable in any type of engine, whether it's a 2-valve cylinder head or 4-valve cylinder head, to run extremely wide coil binds. And I'm talking about triple digits on coil binds where guys are looking at 100,000s, 120,000s before coil bind. That's just not acceptable today, you know, in most applications. You have to keep the distance on most of these newer technology springs very close to coil bind. And I'm talking 40, 50, 60,000s before coil bind. And that's where you're going to draw most of that energy within that valve spring, and you're going to draw it outside of it. And keeping that energy outside of that spring initially will help the stability, will help the harmonics of the valve spring. It will help the longevity as well, the lifespan. We look at sometimes dynamics internally, and the fact is, having such close coil binds, you can increase valve spring life sometimes by 10, 15, 20%, you know, overall. That's huge, you know, that's very large, where that spring is happy. It's not issuing, we call them slinky sometimes, because we'll look at some of the initial springs and you throw a ton of coil bind at them, let's see what happens, you know, and they literally form into a slinky. We start tightening up, and that's the slinky now, and that harmonic instability will start diminishing, and you'll start seeing these colors overall start becoming more of the reddish, the oranges, the yellowish, and really start basically finding a sweet spot, you know, overall on the spring. Dressing the spring is another avenue where we love it, you know, where we put chamfers on springs on the upper bottom part of the spring. Sometimes, you know, cost factor is a point on a valve spring, but, you know, rolling the edges, a lot of valve springs that get manufactured, they get cut right off. You get a sharp edge on either side. You know, high-tech valve springs, very expensive valve springs, you have to radius all those edges through and through. That helps out not only with the spring itself, but it helps out with the dynamics between the retainer and the spring. It doesn't allow the retainer itself, if it has excessive amount of movement, it doesn't allow the retainer itself to embed itself in those sharp edges around that spring. It just literally hugs itself around those radiuses, and that improves it a lot, you know, overall, because there's a lot of misconceptions in the fact that people say, well, titanium retainers, you know, they wear too fast, you know, they're not reliable. Well, if you dress the spring correctly and you have the right details really placing on a valve spring, the retainer itself also designing it correctly around the valve spring. And we call it press fit, right? Where you're putting that retainer on the valve spring and it's snapping in there. There's very little to no movement. Your titanium retainer will have very good life, you know, at that point. Not as good as steel, because obviously it's still a much softer property and material, but it will have very, very good life, you know, overall.
As we're starting to wrap up on time, I think we could probably do this for 3 days and not run out of questions and things to talk about, which is great. But, you know, do also want to let folks know if they're interested in the products that Ferrea has, how can they contact you? Distribution through engine builders directly?
Right. So, you know, guys at Ford Piston, great dealer of ours, as well as they do installation for you. They do the whole engine, if you like. You know, they're a great dealer for us out of Indiana. They deal a lot in the sport compact market. You can deal with them directly. If your guy just building a couple engines, a year, you need Valvetrain components, you can just buy the components from them as well. Our distribution network is very large. We're worldwide. You can buy directly through your dealer if it is convenient for you. In a lot of cases, those dealers have other parts, that you typically want. So they give initial discounts on the whole dollar amount that you're actually purchasing per year. So it ends up working out a little bit better for you. We are a company, and we still stand to be true that we still deal with engine builders. Engine builders are still a lot of our business. We love working with them. They push the envelopes for us. They push us to do better stuff. So you can call us direct as well. You're building a couple engines a year. You just need some technical advice, or you want to purchase direct from us. You can call us direct, and also purchase through our website, which is ferrea.com. You're not going to get the best pricing again, because if you go through a dealer like Piston, you're going to get much better pricing, and you're going to get a lot of tech expertise as well. Something that they may not know, they'll bounce back to us and say, look, we got this guy on the phone. He's asking such and such on this valve material. There's something new that we've come out with. We'll answer that question. He can get back to them, and then we can move forward. But we're very much, we love the phone. I know a lot of companies don't love the phone. We do. You can send us an email and obviously get in contact with us.
And Luke, for Piston and what you do with Ferrea and really what you do for your customers and all of that, is there anything you want to let folks know who might be here on the webinar?
Yeah, best way to get a hold of us for general inquiries, basic questions about engines and parts, probably through our social media is probably the quickest and easiest way. If you have more detailed questions, engine applications, we put engines in everything, whether it's open wheel, Dallara chassis, or Ligier, or dirt cars. We put engines in everything. We have some pretty exceptional engines that race, up to 24-hour races, naturally aspirated up to 500 horsepower and turbocharged to the limit of every part that we put in it, all the way down to just regular, pretty tame raceable products. That's probably best through email. If you call we have people on the phones every day. You're welcome to call. You're probably not going to get me on the phone on a day-to-day, but email you will. So shoot an email to luke@team4piston.com. I can help with the details and also establish a direct line of communication through the phone as well. But mostly focused on 4-valve technology and a lot of inline 4-cylinder engines that we're putting into every type of racing. And we like to win. We like to win more than anything. It's the best thing. So if you like to win, we're your guy.
Awesome. Well, gentlemen, thank you both so much. I do want to also let you know that, if you have any more questions about Ferrea or anything like that, you can always go to Epartrade and go to their page on Epartrade and find out how to contact them directly. But Zeke, Luke, really want to appreciate say thank you for your participation here today, and appreciate everyone who joined. And we still have more, but thank you, gentlemen.